All right. So we talked about some limit laws, which are basically things that we can generalize for limits because it takes a lot of time to graph a function and then do the left-hand limit and then do the right-hand limit. And if they match, then we can say there's a two-side limit that we can talk about. That takes a lot of time. So instead of doing this, we have these laws that make it a little bit easier for us to understand what limits are and find limits a lot easier. We talked about the limit of a constant function. So for example, if we had a straight line, flat constant line at 3, for example, the limit of anything as x approached any number would be 3, right? So the constant function is what we expect. We also talked about f of x equals x. And we said that we could literally just plug in whatever number we're approaching to into x, and then that's our limit, right? So for example, the limit as x approaches 5 of x was 5, just plugging it in. We were working our way towards like mx plus b, for example, and we also figured out that if we had a number like 2 times x, we could take the 2 out of the limit and then multiply 2 times whatever the limit of x was. So we're essentially plugging x into our function as well. Okay, so we had 3 findings. Okay, if you flip the page, I have a couple other findings, and we're not actually going to go through these too much, but this is a theorem of limits. And a theorem is basically something that is always going to be true. It has a proof, so it's very proven that these are true. Okay. I know this looks a little bit funky, but let's kind of just break this down a little bit, okay? Let's say we have 2 functions, f of x and g of x. So they're 2 different functions. They have their own different graphs. And we're approaching a specific x value. So maybe we're trying to find the limit as x approaches 3 or 4 or something of both of these functions. Function 1 has one limit, L1. Function 2, g of x, has L2 as its limit, okay? If we added or subtracted the 2 functions and we took the limit would be the limit of the first function plus or minus the limit of the second function. So if we add limits or subtract limits, we add their respective limits. If we add or subtract functions, we're adding and subtracting their limits, okay? Same thing goes with multiplication. If we multiply the 2 functions, the limit of the multiplication is going to be the first function's limit times the second function's limit, okay? Division's a little bit trickier, not really though. When we divide 2 functions, we're dividing the limits, but we have to make sure the second limit isn't 0 because then we'd be dividing by 0, which isn't really good, right? Okay, so 3 kind of basic laws, pretty easy to remember, right? Okay. Let's kind of put this together. I know this is kind of overkill, but we're kind of going towards something. Let's try to use our findings that we found on the first page and this theorem. Let's say I have a function and the limit as x approaches a of our function f of x is just equal to L now. So no L1 and L2 because that's a little bit confusing, okay? What would the limit as x approaches a of f of x times f of x be? Yeah, L times L or L squared, good. So it'd be L times L or L squared, right? When we multiply 2 functions, we multiply their limits. It works the same if we're talking about the same function, right? What do we expect f of x cubed to be? Or its limit to be? L cubed, right? And I guess L to the 4th, right? In general, the limit as x approaches a of f of x to the nth power, so any power of f of x, is going to be L to the n. I'm not going to prove it for you, but I'm pretty sure we're all convinced that that's true, right? Okay. So putting this together, we know that the limit as x approaches a of x is a, right, from our findings, okay? What do you think the limit as x approaches a of x squared is? A squared, right? Essentially plugging in a, right? And I bet you know what x cubed is? A cubed, right? And if we keep going, the limit as x approaches a of x to the nth power is going to be a to the nth power, okay? So we're essentially plugging in a into x. Okay. I know that was kind of overkill, but I promise I have a point. Okay. Let's talk about polynomials, right? Polynomials are things where we have a bunch of different variables being added together, okay? And let's say I wanted to find the limit as x approaches 7 of x cubed plus 2x squared minus 9x plus 13. I think you can kind of deduce that I'm going to plug in 7 into my polynomial, but let's talk about why that's actually true from the information that we have, okay? Let's see, we have a bunch of functions added together. We have x cubed, 2x squared, 9x, and 13. What can I do with my 3 limit laws that I have to expand this limit? How can I make this a bunch of limits, maybe? That makes sense.
X cubed plus a limit of x approaches 7 to x squared.
And so on, yeah.
Do that for all of them.
Yeah, right. When we add functions, we can add together their limits, right? So I can break this apart, okay, into each of their different quantities. Subtraction also counts, right? So this becomes all of these limits added and subtracted together. Okay, so we're applying those 3 basic limit laws to this polynomial based on the information that we have, okay? All right, it looks like I kind of already know what the limit as x approaches 7 of x cubed is, because that's what I literally found a couple minutes ago, right? What is the limit as x approaches 7 of x cubed? 7 cubed, good, we're just plugging it in, right? Okay. I don't have a rule for this guy yet, but what can I do with this limit to make it into something I can work with? Multiply by 2 or take the 2 out. Was that what you're going to say?
Yeah.
I'm forgetting your name, Blake, right? Okay, cool. All right, I can take the 2 out or multiply by 2, right? So 2 limit as x approaches 7 of x squared, okay? And I'm assuming we can do the same thing with the 9, right? So that becomes 9 limit as x approaches 7 of x, okay? Plus the limit as x goes to 7 of 13. Okay. Now we have very basic limits that we've talked about before. We know the limit as x approaches 7 of x squared can be solved by just plugging in 7. So this becomes 7 cubed plus 2 times 7 squared minus 9 times 7, I guess. What's the limit as x approaches 7 of 13? 13, right? That was the first function that we worked with on the first page. Okay. Okay, so essentially, we basically plugged in 7 into our polynomial, right? So we essentially plugged it in. Plugged in. And I'm very bad with mental math, so I'm not actually going to solve that because I'm kind of lazy. But John might have an answer for me.
391.
391? All right, perfect. Okay. All right, so we've done a lot of work with these basic limits. We know how to take a polynomial and break it into basic limits. And we found out that basically what we did was plug in 7. Cool. Okay. Before I talk about a rule with polynomials, I want to talk about something that you might see in math and physics, in computer science, that might look a little familiar, might not. Okay. This is a template form of a degree n polynomial. Okay, so we know what polynomials look like, right? This is a generalized version of a degree n polynomial. What does degree n mean? What is the degree of a polynomial? What's the degree of x squared plus 2x? 2, good. So it seems like the degree is the highest power, right? This is the highest power of our variable, right? Of x or whatever we're talking about. Okay, so looking at this, we have something c sub n times x to the n, right? This is the highest power of our polynomial, okay? Is there anything I want to say about that? Why can't C of n equal 0?
Because that's just gonna be one.
Not 1, but
Yeah.
0. So if Cn equaled 0, this first term would be 0 times x to the n, which would make there no, x to the n not really exist in that polynomial, right?
Oh,
And then our polynomial would be this, which is a degree n minus 1 polynomial, right? So we don't want C of n to be 0. Okay, so that's definitely true. Cn all the way to C0, all these coefficients are real numbers, so we don't have any imaginary numbers floating around. And the degree DEG of our polynomial is equal to n. Okay, I know this is kind of overkill, but just to go over this, we have an example here, 6x to the 5th. What is n in this example? 5, good. Okay, so I guess we have C5, C4, C3, C2, and so on. What is 6 in terms of C's? C, not quite. It's C sub
And then
n, but what's n?
Five.
5, right? This is C5. Okay, and I guess C, well, let's talk about what C4 is. What's C4 here?
0.
0, right? There's no x to the 4th. So C4 is technically 0. C3 is definitely 0 because there's no x cubed. And then C2 would be 3. C1 would be 2. And C0 would be 1. Okay. Are we all pretty good on notation with polynomials? Okay. All right. So we have a theorem. Instead of going through that whole thing we went through with the other polynomial, trying to find the limit based on those basic little limit laws, we have a nice theorem that tells us if we have a polynomial with the Cn all the way to C0, where all these C's are coefficients, the limit of the polynomial is P of A. Okay. What is that telling us to do essentially?
Plug in.
Plug in, right? Plug in A. Plug in A into polynomial. Okay, so that's all this theorem is telling us to do. If we see a polynomial, we're taking the limit, plug in A. Okay. I'm looking at the time and I don't think we'll have enough time for this proof. If you're in discrete math, this might be a good exercise to go through finding why this works, but it's really not that bad. It's basically what we did on the last page. Okay, so I'm gonna say do if you're in discrete math. Okay. All right, and don't annoy your discrete math teacher because she might get mad at me. Okay. Let's talk about different types of functions. Polynomials are kind of the easy function, right? So we dealt with limits with those. Let's talk about limits of rational functions. Is there anyone who could give me an example of a rational function? Yeah.
X squared minus 16 over x plus 4.
Perfect. Okay, a rational function is defined as a polynomial over a polynomial. So whenever we have polynomials going on in the denominator, that's when we have a rational function. So poly over poly. Okay. So limits involving these types of functions are kind of tricky, and people have different ways of describing this, but I think I've come up with a good way on how to find the limits involving these. And I have like a 3 kind of step method. Okay, so it's a 3-step method. Okay, so what I want you to do is maybe highlight this box here, because this box is going to tell you exactly what type of things to do to find anything involving a rational function, a polynomial over a polynomial. Okay, let's say we're solving the limit as x approaches a of f, which is the numerator, over g, which is the denominator. Okay, so we have 2 polynomials over each other. Okay. First of all, what you're going to do is you're going to just plug it in. Okay, plug a in and see what happens. Okay. Let me just talk about these 3 steps because they're written kind of weirdly. Let's say you plug it in and you get something like 7/5. Okay, the denominator is an actual number and it's not 0. Okay, all you have to do is say that's your answer. Okay, so this is really easy. You just plug it in. Okay. 2, if you get something like this, 6/0. F is non-zero, so you have 6 or -2, something that isn't 0, and the bottom is equal to 0. The function or the limit does not exist. Okay, so all you have to do for your answer is say does not exist. Okay. Let's say you plug it in and you get something like this. You get 0/0. This is when you need to do something a little bit more that involves a little bit more work. You're either going to factor or you're going to do something involving strange multiplication, which I'm going to talk about a little bit later. Okay, so likely you're going to do factoring. If it involves something with a square root, you might have to do some multiplication. Okay, so 3 things that you have to look out for. Both non-zero, plug it in. Denominator 0, but the numerator is not 0, does not exist. And if they're both 0, you have to do something else. Okay, let's do an example here. We have the limit as x approaches -1 of this function. Looking at my rules, I have to plug it in first, right? So let's do plug in. Plugging in. Okay, I don't know why I gave myself such a hard thing to plug in, but let's try this. We want to plug in -1 into our function, right? -1 cubed minus -1 plus 2 over -1 to the 6th plus 3, -1 to the 4th plus -1 squared plus 1. Okay. Some people type in your calculator, that's fine. I think I can do this without my calculator. Let's see. -1 cubed is going to be -1, right? Perfect. -1 becomes +1, and then we've got 2. -1 to the 6 is +1. -1 to the 4th is just 1, so I'm just going to add 3. We've got -1 squared, which is 1, and 1. Okay, so I hope you're getting the same thing as me. I'm getting 4/6. Right, cool. And we can even simplify that to 2/3. Okay.
Where are you getting the 4 from?
Oh, God, I did this wrong. 3/6? I did not actually do that in my head. You're gonna fire me, I swear. 2/6, right? All right. We got 1/3. I'll say I did that on purpose, but I didn't. I'm very bad at mental math. Okay. Are we all agreeing on 1/3? Okay. Taking a look at our 3 types of funky functions, is this type 1, type 2, or type 3?
Type 1.
Type 1, right? We plugged it in. We don't have any zeros going on. So our final answer to our limit is actually just 1/3. Okay, so all we had to do here is plug it in. Okay. And hopefully you won't make as many mistakes as me when I do mental math. All right, let's flip the page. That was pretty easy. Let's do example number 2. Okay. So we got x plus 5 over x squared minus 4. Let's plug in and see what happens, right? Plug in. All right, we got 2 plus 5 over 2 squared minus 4. I think on the top that gives me 7. On the bottom, 4 minus 4. 7/0. Type 1, type 2, or type 3? Type 2. And what does this limit equal? Does not exist. This limit does not exist. That's it. Okay. Oh, yeah.
For the ones that don't exist, aren't you also able to like put it on like a number line and see if it approaches negative infinity or positive infinity?
Yeah, I think we'll talk about that later. That might come up a little bit later. For now, let's say it does not exist, and then we'll see about what the function does. But yeah, that's a good observation. I'm going to put a little star here, just to remind myself. Okay, nice observation there. Any other questions about example 2? Sounds good. All right, let's go to example number 3. Let's see what we can do here. Okay, let's plug in. All right. Let's see. We have 3 minus 3 over 2 times 3 squared minus 5 times 3 minus 3. Okay. We've got 0 on top. 18 minus 15 minus 3. I think we've got a 0 over 0 here, right? So this is gonna be a little funky one. Okay, so I didn't tell you exactly what we need to do. Any ideas on maybe what we can do here?
Factor of the denominator.
Yeah, the denominator has a quadratic in it, and it seems like we can factor this. Now, I know some of you can do this in your head. I have a more systematic way in factoring, so just bear with me while I do this. But when we factor the denominator, we're going to factor 2x squared minus 5x minus 3. We need to find two numbers that add to what number?
Add to -5.
-5, and multiply to what number?
-6.
-6, right? What two numbers do that? If you can do this in your head, don't worry. I'm doing the splitting the middle term version of factoring. What two numbers add to -5 and multiply to -6? Michael.
It, so 2 times -3. And then
Okay.
1.
And then you said 6 and 1?
Yeah.
Okay, yeah, so 2 times -3, they do multiply to -6, but they don't add to 5, so that wouldn't work. But -6 and 1 do add to -5. Okay, if you can do this in your head, don't worry about what I'm doing. But if we wanted to factor this, I would take my 2x squared, split up the -5x into plus x minus 6x, right? Minus 3. Okay. All right. Once we do that, we can split it in half. What do 2x squared and x have in common? They both have an x, right? Okay, what does -6x and -3 have in common? -3, good. What happens if I take 2x squared and take out an x, divide by x? What am I left with? Okay, 2x, and then the x take away an x is a +1. The same thing happens on the right-hand side, right? 6x divided by, or -6x divided by -3 is 2x. -3 divided by 3 is 2x, okay? And then we can combine together. So what are my two factors here?
-3 and 2x plus
2x plus 1, perfect. So this is a more systematic way to factor funky quadratics. If you're fine with doing this in your head, go ahead and do that. Okay. Once we found our factor, let's go back to our limit, okay? So we have the limit as x approaches 3 of x minus 3 over, well, I'll just write it again, 2x squared minus 5x minus 3, okay? Now what I'm going to do is I'm going to replace my denominator with the factored version, okay? And I can put an equal sign between this because the denominator is staying the same, right? So this is the same as x minus 3 times 2x plus 1. Okay, these two things are equal. Okay. Anything I can do here?
Take out the x -3.
Yeah, we can cancel out the x minus 3's, right? Because they're the same on the top and bottom. Sounds about right. This becomes the limit as x approaches 3 of 1 over 2x plus 1. Okay. All right. Now what can we do?
Plug in 3.
Yeah, we can plug in 3. Let's see what happens when we plug in. I'll do it on the side here real quick, just to make sure I can write an equal sign. We got 1 over 2 times 3, which is 6 plus 1. That's giving me something as a number over a number, right? So I can say that this equals 1 over 7. Okay. So even though we started with a limit that gave us a 0 over 0, by factoring the denominator and crossing out the top and bottom, we were able to get that limit at the end. Okay. Any questions on example 3? Perfect. All right, if we flip to the back of the first page, we have example 4 and 4.5. I'll give you a few minutes to work on both of these examples, and we'll come back in a tiny bit. So talk about these. Example 4, I think, is up. I'm actually going to take pictures of this for the video. Yes. There we go. All right. God, I'm forgetting these. Blake, you wrote up example 4, right?
Yeah,
Do you mind kind of taking us through this one?
yeah, so I just plugged in 1 into Axis. You have 1 plus 3 over 1 squared plus 1 minus 2. And that would be 4 over 0. Does not exist.
Okay, so with these guys, all you have to do is plug in, if there's a 0 on the bottom but not 0 top, does not exist. All right, let's talk about this one. Michael, right? Do you want to talk about how you got example 4.5? And I might need to show a little bit more steps here, but why don't you take us through what you did here?
Well, in the beginning, if you just plug in -2, it's 0 over 0. So you just have to factor the bottom, 2x plus 1, -2, and we cancel. And then 1 over 2x plus 1. So you plug in the -2, and you get -1/3.
Nice. Now I'm not gonna, I would never take off points for this. Some teachers, if you go on to Calc 2, might be a little bit nitpicky about notation. They might want you to write the limit sign for each of these. I'm not gonna care, but some teachers might. But nice job there. Does anyone want to see how we factored the denominator? Yeah, let's go over that. Of course, if you can do this in your head, I would never take off points for like not showing how you factored. But the way I like to factor the denominator, okay. Okay, let's just go over how we did this one. We want to find two numbers that add to which number? 5. We're looking for two numbers to add to the middle number, which is 5. And we want them to multiply to what number? 4, right? We want them to add to the middle number and multiply to the first times the last number. We want A times C for numbers to multiply to, okay? What two numbers multiply to 4 and add to 5? 4 and 1, good, okay? So just like I did with the last example, we're going to take the 2x squared, split up the 5x into 4x and x, and then leave that last constant the same, okay? We can split this into half because we can factor by grouping, right? What do 2x squared and 4x have in common? 2x, good. Okay, take 2x squared and take away a 2x, what am I left with? X, okay, and plus 2, good. Take 4x, take away 2x, and we're left with a 2. And what can I take out of x plus 2? 1, right? They don't really share anything. I can take out a 1 though. And well, x plus 2 will stay the same if I factor out a 1, okay? So my final two factors are, well, 2x plus 1 and x plus 2. Okay. So if you're ever confused on how to factor something like this, you can always go through this sort of systematic way to get these factors. You don't have to do it in your head if you don't feel comfortable doing that. Okay. Any other questions about example 4.5? All right. Now I talked about factoring with that weird third type of limit. And I also mentioned that with those weird limits, we can do strange multiplication, which I haven't really talked about. And strange multiplication shows up when we have these pesky little things called root functions. Okay. So I know it looks kind of strange, but root functions are basically square roots, third roots, fourth roots, things like that. Okay. Now limits, Also, unfortunately, we want to find limits of these root functions, but they're not that bad, okay? I have a bunch of stuff here. Let's say the limit as x approaches a of f of x equals L. So L is our limit of our function. This theorem or statement or whatever I'm going to call it says that if I take the square root of f of x, the limit as x approaches of a of that square root is the square root of L. Okay, so I can literally just plug in a into the function. Okay. Okay, same thing with third roots, same thing with fourth roots, and so on. Okay, so square roots aren't that bad until we stick them in the denominator, which we'll talk about a little bit later. Okay, so example number 5, let's find the limit as x approaches 2 of x plus 5. What do we think that's going to be? Square root of 7 or 2 plus 5, which is the square root of 7. Okay, so we essentially just plugged in to the square root. Okay. The square root can also be on the top. Okay, that doesn't really change anything for us. We still have a rational function, so we can try to plug in. Okay, so we can try to plug in negative 125 into this function. It involves a denominator and a square root. We're kind of sneezy today, aren't we? We got the third root of negative 125. We've got negative 125 plus 2. I'm taking the third root of a negative number. Is that okay?
Yes.
Yes, right? Okay, but I still have to keep the negative sign. What's the third root of 125? 5, good. Or 5, right? Okay, I'm not good at mental math, so gotta have you guys check me. It's actually, yeah, it's actually going to be negative. When we take an odd root of a negative, the negative stays as it is. Negative 125 plus 2 is negative 123, right? So we're left with 5 over 123. This is a type 1 limit where we just plug in and our answer is what we plugged in because there's no zeros. Okay, let's see if we have enough time for the next one. Let's start the next one. We might not finish it. Okay, we've got x minus 1. We've got a square root in the denominator, which is kind of messy. Let's plug in and see what happens. So let's plug in. Okay. First of all, we've got 1 minus 1 over the square root of 1 plus 3 minus 2. Okay. On the top, we've got a 0. 1 plus 3 is 4. Okay, the square root of 4 is 2. So we've got a 0 over 0 type limit. Okay, gets a little bit tricky, and I don't think we have enough time for this, and we still have to do a quiz review. So I think we're going to leave it on a cliffhanger here. We'll talk about what we do with these next class. Yeah, okay. So I think it's about quiz review time. All right. If you are looking for the quiz review, it is on the modules page and you scroll to the bottom, okay? But I have it printed out for